Hello. Hope you're doing good today. We are going to be talking today about free body diagram and particle equilibrium. That's the main topic that we are going to be covering today. The objectives for today's lecture, at the end of the lecture, you should be able to draw a free body diagram and apply equation of equilibrium to solve the 2D problem. So we're going to basically be working in 2D and how to create a free body diagram in order to solve a problem in equilibrium. Now, first of all, quick question. When a particle is in equilibrium, the sum of the forces acting on it equals, and you have to choose the appropriate answer. I'm going to give you 5 seconds just to think of an answer, but please do it. Don't just wait for me to tell you the answer. Think, and what do you think it's going to be? Well, think about it. If it's in equilibrium, that means that there is not going to be unbalanced force. But that means that the resultant force, the sum of the forces, has to be equal to 0. That would be the correct choice. This is another problem, another question that usually students have trouble, not because they don't know it, but basically because they don't remember that they know it. And they forget about clue words. When they say for a frictionless pulley and cable, tensions in the cables T1 and T2 are related as, usually people say, or some of the students say, that T1 is bigger than T2. But that's not correct, because of it says frictionless pulley. So whenever you have frictionless pulley, the tension here and the tension here has to be exactly the same tension. Applications of free body diagrams, well, you have that real life situation, and even though it's not 2D, it's a 3D problem, but this part can be simplified as a 2D situation. So you have that problem, but okay, I have this spool here, but I want to know how much is the force in each one of the cables, how much is the force in this bar, in this cable, this cable, this cable here, how much is the total force here. And in order to do that, I have to apply equilibrium. Another example similar to that one. What is the maximum weight that can be lifted in this situation? If I know the strength of the cables and the angles, of course, and the geometry of that problem. This is a typical problem of traffic lights also. What is the size of the cable that I have to use here? Of course, for knowing the size of the cable, you need the extra component, which would be the manufacturer type of cables for a particular tension, but definitely I can calculate the tension in these cables by applying equilibrium. Now, free body diagram. The first thing that we have to know before applying, before even trying to get a free body diagram or going into that concept, is that if you have a whole system and the whole system is in equilibrium, every part of the system must be in equilibrium also. That's the key. If the structure is in equilibrium, every single part of the structure is in equilibrium. Or you can say otherwise also. You can say if one part of the structure is not in equilibrium, that means that the structure is not in equilibrium. That means that if the whole structure is in equilibrium and we study this particle here, and we do somehow that we're going to be discussing now a free body diagram around that point, that should be in equilibrium, and that is the key for solving this situation. Free body diagrams, we have to know how to draw it and how to use them. First of all, what is a free body diagram? Free body diagram is a drawing, simplified drawing of course, that shows all the external forces acting or reacting in the structure and all the dimensions and all the information that you need. Basically, that's a free body diagram, where the forces are located, how much is the value of the forces, or the nomenclature of the forces if you don't know it. Why do you do a free body diagram? Well, you do a free body diagram first because it shows you a simplification of the structure, and secondly because it helps you to create the equilibrium condition so you can set up the equation of equilibrium and solve that particular problem. How do you do a free body diagram? Well, first of all, you have to see the point that you want to do free body diagram. If the point that you want to do is this point, first you imagine that particle isolated, and then you start showing all the forces acting or reacting in the particle. Remember, active forces are the forces that want to move the particle, and reactive forces are the forces that try to hold the particle into place. You have to show the forces that you know, the values that you don't know, the directions, the angles, the names, etc. How, if we have to do a free body diagram of this situation, let's say that you know that an engine with a mass of 250 kilograms is hanging here from these ropes, from these cables, and we want to calculate how much is the tension in each one of the cables. In order to do that, of course, we have to do a free body diagram of this structure. So the first thing that we're going to do is set up an axis of reference. If we are dealing with particle equilibrium, the best place for setting up your reference is at the point where you want to do the equilibrium. Secondly, you're going to isolate that point. You're going to make a circle. You're going to make a shape around that point. And once you do that, you're going to start cutting out the cables one by one, the other forces, and eliminating this part like that. But if we eliminate that part in this diagram, it has to be a force applied in this cable that holds it together, and that force is going to be acting in this direction. If I cut this and eliminate this part, the force AD is going to show here. And same thing, once I eliminate this, I'm going to have a force acting here. What is going to be the force acting in this cable? Well, the force acting in that cable is going to be what? The weight of the engine, which is no other thing than mass times gravity. And that's going to be the value for this force AC. Now, there you go. Now we have equilibrium. Now think of that particle. That's a particle. That particle can move either in the X direction or in the Y direction. Of course, it can move in combination of X and Y, but it's the same thing. So the possibility for this particle not to be in equilibrium is either the particle is moving in this direction or the particle is moving in this direction. That means that for this body to be in equilibrium, or this particle, because it's not body, it's a particle, for this particle to be in equilibrium, that means that you shouldn't have any unbalanced force in X, and in the same way you shouldn't have any unbalanced force in Y. If we do that, then what you have is this: summation of forces in X equals 0 and summation of forces in Y equals 0. If we do summation of forces in X equals 0, we have to think of this force. The first thing that we have now is a force acting in a component of this force acting in this direction. We're gonna see that summation of forces in X. I'm saying everything that goes to the right is positive, but this convention is yours. You can do any convention that you want to here. So if we do that, I'm gonna do summation of forces in X equals 0. That means that I'm gonna have a component of this force acting in X. What is the value of this component acting in X? Well, it's going to be TV cosine 30 degrees. And it's positive. What other force do we have in X? We have the force TD. And that force is a negative force because if I say everything that acts to the right is positive, this force is acting to the left. That means it's going to be considered negative force. So we have TB cosine 30, which is this one, minus TD equals 0. And you have your first equation of equilibrium. And in this first equation of equilibrium, you have two unknowns because you have TB and you have TD. Now we set up the other restriction for equilibrium, the other equation. Summation of forces in Y has to be 0, must be 0. So we're going to do summation of forces in Y, which we have only two forces acting, we have the vertical component of this TV, and that vertical component is going to be this one, which is basically TV sine of this angle. Of course, this force is not acting here, it's acting at the particle, but this distance and this distance are the same, so the value of the forces are going to be also the same. So, and it's positive because it's pointing up. And this other force that we have here is negative and it's acting downward. So our equation of equilibrium is TV sine 30 minus 2.452 kilonewton equals 0. From here, this is not even a system of two equations with two unknowns. This is just basically, I can solve TV from this equation by passing this to the other side and divide by sine 30, which gives us a value of TV of 4.9 kilonewton. And then what do? Well, you have the other equation. You get this value of TV, plug it into here, and solve for TD, and get your value for TD. If you study this problem and you go back and you really analyze what we did with this problem, you have to realize that I can set up in equilibrium in 2D, in a particle equilibrium, two equations. Summation of forces in X has to be 0, summation of forces in Y has to be 0. That means also that the maximum amount of unknown forces that we can have at this level, at the statics level, is only 2. You can't solve immediately a problem where you have 3 unknowns because we don't have the tools. When that happens, you have to use other type of situations and you have to use compatibility equations, which hopefully you will learn starting that in mechanics of material or mechanics of the formable bodies. But for the time being, just think particle equilibrium in 2D, maximum of 2 unknowns because we only have 2 static equations. What are those 2 static equations? Summation of forces in X equals 0 and summation of forces in Y equals 0. Okay, now we're ready for something a little bit more, I won't say complicated, but let's say that we have to work a little bit more. Now we have this nice example here, and it says each cord can sustain a maximum tension of 200 pounds. Determine the largest weight of this sack that can be supported. Also determine the angle of the cord DC for equilibrium. And then you start thinking and you say, oh my God, look at that thing. How many unknowns I have? I have 1, 2, 3, 4, 5, 6, 7 unknowns. And I cannot solve that. No, yes, you can. But you can't see all the unknowns at once. Remember the basic principle that I told you before? If something is in equilibrium, a body is in equilibrium, a system is in equilibrium, every single part must be in equilibrium. So we have to start looking at this problem not as a complex problem, but just as a combination and superposition of several simpler problems. I'm going to explain myself. The only thing that makes this problem even a little bit more interesting is that actually what we have to calculate is the weight of this sack. And this value of 200 is not the value of any tension, it's the maximum value that one of those let me put it in this way, is the maximum value that you can have applied to any of these forces, that can take any of these forces in order for the system not to collapse. So we have to do an equation of equilibrium. Where do we have to apply our free body diagrams? Everywhere. We need a free body diagram here, 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 and here. And if we do that, we have to draw circles, 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 and circles, and split everything in a way that is going to look pretty much like this. I don't know the weight. So what we're going to do is we're going to express every single one of those forces in terms of that weight, which is my basic unknown. And let's start with this part here. if I start with this part, I can apply summation of forces in Y for this, let's say, part of the system. If I say summation of forces in Y equals 0, what do you have? TH minus W equals 0, or you can say immediately that TH is going to be equal to W. And we're going to express that tension, as I told you, in terms of W. Now, we assume that we know this W. This W, even though it's an unknown, because of the fact that we are expressing everything in terms of W, I'm not counting that as an unknown so far. So how many unknowns if I study this system? Well, I know TAH because I already calculated in terms of W. My only unknowns are TAB and TAC. So we can go here and say, for example, summation of forces in X equals 0. If we say that, we're going to have the X component of TAB acting to the left. And remember, acting to the left in this case means negative, because she's acting in this direction. So it's going to be negative TAB cosine. Why cosine? Because we are looking for the adjacent to the angle, the component of the force adjacent to the angle. So it's going to be negative TAB cosine 45 plus TAC sine 60, also adjacent, but this time to the right, equals 0. That's the first equation. I have two unknowns. I can't solve it like that. Now I'm going to go for the summation of forces in Y equals 0. If I do that, then I have this component. This component is positive because it's pointing up, and it's going to be TAB sine of 45 because I'm looking for the opposite to the angle, plus again is pointing up, TAC sine of 60 minus TAH equals 0. You can ask me and say, or you can ask yourself and say, how do I know that these forces are pointing in those directions and not coming in? And I can give you every sort of answers and tell you it doesn't matter, because at the end, if you get a negative value, that is going to tell you that the force is opposite to the value that you assume, and that's correct. But you have to be more practical and more logical with these type of situations and think, what type of structures are these? What type of elements are these? Those are cables. Have you seen in your life any cable that push? No, cables don't push. If they were rods, steel rods, it's different. Those are cables, so the only thing that a cable can do is pull. Hence, all the cables have to be pulling the particle, no matter what. You can have 0, but never you're going to have a negative value for a cable, because the cable don't push. Okay, so I have two unknowns here, TAC and TAB cosine 45, cosine 45. Remember, TAH I know it because it's W, so I'm going to plug this into here, and then I have these two equations. How do you solve these two equations? It's up to you. If it was me, there are some calculators that solve it, of course, but not the normal TI, the 80T or the 84 that you use, because we are working with literal equations. So you have to remember your methods for solving a system of equations. You can solve for one variable and plug it into the other one and go and solve it. But if you look at these two equations, be a little bit smarter and say and think, oh, look at that, negative TAB cosine 45 plus TAB sine 45. Cosine 45 and sine 45 they are the same value, square root of 2 divided by 2. So what if I add term by term the two equations? If I do that, this and this term are going to cancel out, because this is negative TAB cosine 45, positive TAB sine 45. This and this cancel out. Basically, my only unknown is TAC. I can solve for TAC. Once I know TAC in terms of W, of course, I plug it into either of the equations. This is the easiest one, and I solve. I solve for TAB. Now we know TAH, TAB, and TAC. Where can we go? Well, let's go to this one. If I go to this one, how many unknowns do we have? I know this one, and then I have one unknown and two unknowns. That's not correct. We have one unknown, two unknowns, but we don't know this angle also. So basically we have three unknowns. That means that we can't move to this side yet. Then I have to move to this other side and do equilibrium in this particle, in the particle B. If I go to the particle B, I know TAB, and then the only unknowns are TBE and TBC. If you check these, it will be easier to start with summation of forces in y equals 0. Reason for that, in y, my only unknown will be the y component of this force, because this other unknown doesn't have any y component. So I'm going to do summation of forces in y equals 0, and the y component for this force, TBE, is going to be TBE sine 30. So positive because it's pointing up. Once again, what we have here then is TBE sine 30, why sine? Because it's the opposite to the angle, sine 30, minus the y component of TAB. The y component is this one here. And this component will be then, if this is 45, this angle here, that means that this component is going to be negative because it's pointing down, and it's going to be TAB sine 45. And then you get your first equation. Do you know any? Do you know TAB? TBE, I mean. No? Do you know TAB? Yes, we do. It's here. So I'm going to get this TAB now, plug it into here, solve, and calculate TBE, remember, in terms of W. And now we can establish summation of forces in the x direction, in this direction. If I do that, this component for TBE is going to be TBE cosine 30, and remember it's pointing to the left. So then it's going to be negative TBE cosine 30 in this direction, plus TBC, this is acting in the x direction, plus the x component of TAB. The x component of TAB is going to be this one here. That means it's adjacent to the 45 degree and it's pointing to the right. So it's going to be plus TAB cosine 45. And then you get this equation. Out of this equation, I already know TBE because I calculated. And I also, remember, we know TAB from here. So I can solve for TBC by knowing those two. Plug these two into this equation and solve for TBC. So we're almost done with this problem, guys. The only thing that we have to do now is go into the particle equilibrium at C. And what are my unknowns at C? I know TBC, I know TAC, and my unknowns are going to be TCD and the angle theta. So let's go and let's start by doing summation of forces in x equals 0. I have negative TBC. Any other thing acting on x? Yes, I have the horizontal component of TAC. Remember, the horizontal component of TAC is adjacent to this angle here, 60, unless you want to use the vertical, but I have already this angle, so it's going to be negative because it's going to the left. This one, remember, to the left. And is adjacent to the 60 degree angle, so it's going to be minus TAC cosine 60 plus TCD because it's going to the right, and it's adjacent here, cosine theta. So you have that expression, that equation. And now you do summation of forces. Well, basically you know this and you know this, you plug them in and you simplify your equation. You can remember cosine 60 is a number, it's 0.5. You can multiply 0.5 times this and add it with this one, and then you have an equation, but your unknowns are still going to be TCD and cosine theta. When you do summation of forces in y equals 0, then you have the y component of this one is TCD sine positive, and the y component of this one is TCD sine 60 negative, TAC sine 60 negative. So you have this equation. You know TAC from before, you plug it into here, So basically look at the two equations that I have. I have these two equations, and my unknowns are TCD cosine and TCD sine. If you are starting using substitution, it's going to take you forever. You can use trial and error if you want to, and you know how to for solving it. But once again, be smart. What if I isolate this term and I pass this term to the other side of the equal sign, and I isolate this term also, and I pass this to the other side of the equal sign? Then I can divide this by this. If I do that, term by term, of course, TCD and TCD cancel out, and sine divided by cosine is tangent. So I have an equation that is going to allow me to calculate tangent zeta, because the W's are going to cancel also, and I can calculate the angle. Once I know the angle, I just plug it into here, and I can calculate TCD in terms of W. Now, do you remember what the problem was asking us to do? The problem was asking us to calculate the weight of the sack, W. And we haven't done that. We just got a bunch of tensions in terms of W. But look what we got. We got a bunch of tensions in terms of W. But we also know what is the maximum value that those tensions can have. So I can start with this one and say 200 equal this times W, and calculate the W. 200 equal this times W, and calculate the W, and so on. And at the end, I have to select the minimum weight. Why the minimum weight? The minimum weight is going to be corresponding to the force or the tension AH. Now the minimum weight is going to be 200. What happens if I don't do that? Let's say that I put 200 here, and I say, okay, this TBC can hold up to 200. So how much is the weight? It's going to be 200 divided by 0.2679. I don't know how much is that. It's going to be like 800, close to 800. So the weight is 800. If I put that weight in any of these equations, these tensions are going to be bigger than 200. That means that they are going to collapse, they are going to break, and the system is going to just fail. So usually when in this type of designing problems, when you are looking for the maximum, it's going to be the minimum of all the values that you find, usually. Now look at the other particularity of this problem. The other particularity of this problem is that if you look back to the problem, let me go back to the problem here. If you look back to the problem, you could have seen it, because it was obvious that this tension was going to carry the whole amount of weight. So if 200 is the max, the other tensions are just share. The other weight is distributed and is affected by angles, but the whole share of the weight is taken by this tension. So you could have seen it. But if you say that is the answer, you have to really justify your answer very good. With words, I mean. And I don't care, I will give you credit for the problem, full credit for that problem. Usually, I don't incorporate this tension into the solution of the problem, and I say these tensions actually are the ones that you have to check for the weight. And our result was this one here. That would be the other one, the CD. If you look closely here, TCD is the one with the biggest coefficient. That means that it's the one that is going to give us also the minimum weight after this. I mean, if you don't take this into account, this would be the answer for that problem. That's a cool problem. That's a very nice problem that involves a lot of calculations, a lot of tricks in order to solve systems. And the other point that I want to talk to you today is about springs, cables, and pulleys as part of equilibrium also. And you know springs, you know the constant of the springs. What is the only difference? What is the only new addition to this type of problems? That then the force is going to be the constant of the spring, or the stiffness is called also the spring, times the elongation or times the deformation of the spring. And you know that from physics that you took it before. And the other part could be pulleys, and that's why I incorporated this question at the beginning of the lecture. Basically, you have to know when you have a pulley, and it's frictionless. A small pulley is another word that usually is used for when you want to refer to frictionless pulley, you also refer as small pulley. When you do that, remember the tension is the same on both sides. It's the same tension. It's a continuous tension. If you have friction in the pulley or the pulley is big, then these tensions are not going to be the same. They are going to be affected by that. But in our case, that's not going to happen. So look at this other problem. You have several problems like this, and when you see that problem, it looks like something alien, something extraterrestrial, but it's not. It's something fairly easy to do if you put all the concepts together. A continuous cable of total length 4 meters is wrapped around the small pulleys. Once again, small pulleys means frictionless pulleys. That's why you have that word over there at A, B, C, and D. If each spring is stretched 300 millimeters, determine the mass of each block. That means that you know the stretching of the spring and you know the constant of the spring. That means that you know the force acting here. That's why you know the stretching of the spring. Neglect the weight of the pulleys and cores. And now you have another piece of information here that says the springs are on a stretch when D equal 2 meters. So originally the system is at rest like that. This is 2 meters. And now I'm going to stretch. Why this is stretching? Let's see why this is stretching. I'm going to just come here directly and then I'm going to go back. This is stretching because these weights here are going to be going down. When this weight is going down, this is going to come in this direction. And when this is coming in this direction, in both sides, this other part, the part of the spring, is coming down. That's the stretching that we are referring. So that means that this distance, the originally 2, now gets reduced. Gets reduced in how much? 300 millimeters here and 300 millimeters here. That's the key for solving the problem. Now let's go back and let's start from the beginning again. Now let's start with what I know, what we know. We know that force is the stiffness constant times the elongation or times the deformation of the spring, Kx. I know the 500 stiffness constant or the spring constant multiplied by elongation. How much is the elongation? 300 millimeters, 0.3 meters. That means that the force here is going to be 150 newton. But the force here is the same force here also because everything is symmetric. So that means that I can do an equilibrium around this particle A. If I do that, then you're going to have tension, 150, and angle theta, and angle theta, which I was going to say I don't know, but yes, we do know. We just don't know that we know it. This angle theta and this angle theta. If I do summation of forces in X, the only thing that I'm going to find is that this tension equal to that tension, and we already knew that because this is a frictionless pulley. But if I do summation of forces in Y, then I'm going to get that this T times sine theta plus this T times sine theta minus 150 equals 0, or 2T sine theta equal 150, or T is 75 divided by sine theta. And then we get an equation here with two unknowns because we don't know T and we don't know theta, but we're going to know that. Now let's go again to what we said before. He said when on a stretch this is 2 meters and then all the stretching happened. Look at this part, look at this diagram here. If I look at that diagram, what I have in reality, there's another piece of information that says that this distance is 4 meters. And if this distance is 4 meters, then you have 1, 2, 3, 4 meters. That means that this distance is 1 meter and this distance is 1 meter here. Originally, that was the position for this point. Now, when this is a stretch, this point moves to this part. Now, there's another thing that you have to assume. another assumption that you have to make, that these cables have to be an extensible cables. These cables, because if those cables can stretch, then the problem acquires a whole new, horrendous new dimension. So these cables are unstretchable. They are not going to change the length. If this is 1 meter, that is going to be all the time 1 meter. The only thing that is going to go is going to change in this way, but it's going to be always the same length. If that is happening, then you have, originally that was 1 meter and 1 meter, meaning 2 meters, but now this spring stretch 300 millimeters, 0.3 meters, meaning that the final distance from here to here is 0.7. So you know this distance is 0.7, you know this distance is 1, you can calculate the angle. An angle is going to be, I don't know, sine of the angle is going to be 0.7 divided by hypotenuse. If you have that, you already can solve for the angle, calculate the angle, and once you have the angle, remember you have the equation here, and once you have the equation there, you can calculate the tension with that angle. Basically, I have the problem solved. The only part is that I know now this tension and this tension, and okay, I'm sorry, I have to close the door because somebody was talking too loud. So I have this tension and this tension here, and I can do summation of forces in x equals 0, and if I do that, I can find this tension in this core. Summation of forces in x, I'm going to have 107 cosine 44 plus 107 cosine 44 minus T2 equals 0. Solve for T2 in terms of Newton. Then I have T2, and the only thing that I have to go is to the final part. Remember now the problem was asking us what is the mass of these objects, and because this is a frictionless pulley, this tension has to be equal to this tension, meaning M times G is going to be equal to 153 divided by G, 9.81 meter per square second, and get the mass of each one of those objects. And that was basically what the problem was asking us. I'm going to advise you to go back and review this problem and the other one, of course. Review the lecture. I'm going to post the lecture for you, of course. Go and review it. And then go to your book or books and start working and dealing with that type of problems. If you have any doubt, you know that you always can come to me and use any other resource that you have available here for you. Next lecture, we're going to be working in 3D now, and it's going to be basically the same with the addition of the extra component, which is the third dimension that we're going to incorporate to the problem. So I see you next class, guys. Thank you for watching, and have a nice day.